If you've been keeping up with all the video lessons in this unit of study, then you've seen what happens when a dielectric slab is inserted between the plates of a parallel plate capacitor with a plate separation of D and an area of A. Now, this capacitor, if it's filled with air, has a capacitance equal to epsilon naught times A over D. I'm going to call that C naught. I want to see in this case what happens when, instead of putting dielectric material in between the two plates, what if we take a very thin metal sheet and we place it halfway between the two plates? So let's consider that maybe this capacitor, before that metal slab was even inserted, this capacitor was hooked up to a battery. The switch was closed and the capacitor was then charged up. It reaches electrostatic equilibrium and then the switch is pulled back open again. And then the metal slab is inserted. So the charge that exists on these plates induces a charge on the thin metal sheet. After all, because it's metal, it has free electrons, and so those free electrons are going to accumulate across the top surface of this thin metal sheet because they're attracted to the positive and repelled by the negative. And so the thin metal sheet has a negative surface charge density across the top and a positive surface charge density across the bottom. So effectively what we really have here, it's as if there are now two parallel plate capacitors connected in series. They have the same area A, but each one has a separation then of D over 2. So we might call the top one C1 and the bottom one C2. Well, the capacitance for C1 is epsilon naught times A over D over 2. Or in other words, 2 times epsilon naught A over D. Or in other words, 2 times C naught. And the same thing for capacitor number 2. Its capacitance is also 2 times C naught. And because they're connected together in series, we can use the rule for equivalent capacitance for capacitors in series. When there's just 2, we say we take the product over the sum. So 2C naught times 2C naught divided by 2C naught plus 2C naught gives us 4C naught squared over 4C naught, which just reduces to the original capacitance. Point being, there's no change in the capacitance if you insert a thin metal sheet halfway between the plates. Of course, that piece of metal doesn't have to be thin. It could have some thickness here indicated by T. So now what happens if we take the metal and put it between the plates of the already charged capacitor? So if this capacitor already had a charge of the positive on the upper plate and negative on the bottom plate, the same thing takes place. The free electrons in the metal slab accumulate across the top surface, meaning the top surface is negatively charged, the bottom surface is positive. Now the space between the top plate and the top surface of the metal slab isn't D over 2, it's D minus the thickness of the slab over 2. And the same spacing between the bottom surface of the metal slab and the bottom plate. So again, it's as if we effectively have two capacitors connected in series with the same area as our original capacitance, but different plate separation. So we can call these C1 and C2. Of course, C1 is going to be equal to C2. In fact, C1 is equal to epsilon naught times A over D minus T over 2, or 2 epsilon A over D minus T. That's also the value of C2, and so the equivalent capacitance is equal to 2 epsilon A over D minus T multiplied by another 2 epsilon A over d minus t product over the sum. 2 epsilon A over d minus t plus 2 epsilon A over d minus t. So we got 4 epsilon squared A squared over d minus t quantity squared, all divided by 4 epsilon A over d minus t. So the 4 cancels, you cancel one of the epsilons, cancel one of the a's, cancel one of the d minus t's, and we get the equivalent capacitance is epsilon naught times A over d minus t. Now our original capacitance before we inserted the slab was epsilon naught times A over d. So we can see that as long as t is non-zero, that the equivalent capacitance is going to be greater than the original capacitance. So there is an effect on the capacitance if you insert a piece of metal and the metal has some thickness that's non-negligible. Now wait a minute. We didn't have to insert the thin metal sheet exactly midway between the top and bottom plates. We could have put it a little off-center, so that the distance between the top plate and the thin metal sheet maybe is something we call A. Then the distance between the metal sheet and the bottom plate would be d minus A. Well then, does that have an effect on the capacitance? Let's find out. So again, we draw it here. So say maybe this is A, and this has to be d minus A if the original plate separation was d. One more time, it's as if we have two capacitors connected in series, a C1 and a C2. The original capacitance we call C naught was epsilon A over d before the metal sheet was inserted. So capacitance number 1 would be epsilon naught times area over lowercase a, and capacitance number 2 would be epsilon naught times area over the quantity d minus a. So our equivalent capacitance is C1 C2 over C1 plus C2, or in other words, the equivalent capacitance is epsilon naught A over lowercase a multiplied by epsilon A over quantity d minus a, all divided by epsilon naught times area over a plus epsilon naught times area over quantity d minus a. So the numerator gives us epsilon naught squared a squared over a times the quantity d minus a. And the denominator, well, let's see, this is the same thing as d minus a over a times d minus a. We're just making a common denominator in the denominator, right? Okay, so now we have d minus a plus a times epsilon naught times area all over a times d minus a. So that quantity is in the denominator of the numerator and the denominator of the denominator. I know a very complex fraction here, so it cancels out. One of the epsilon naughts cancels, one of the powers of a cancels out, and then of course d minus a plus a just gives us d. So lo and behold, once again, the equivalent capacitance is epsilon naught times a over d, meaning it's the same thing. So it doesn't even matter if the thin metal sheet is placed off-center. Putting a thin metal sheet in the space between the parallel plates has no effect. Now, what's the point of all this? Well, it allows us to imagine a situation where we can make half-filled capacitors. Let me show you what I mean. So instead of filling a capacitor completely with dielectric, something like this, right, where this pink material represents some dielectric with some constant kappa greater than 1. No. Instead, we can make it so we only halfway fill it with dielectric. So that thin metal sheet doesn't make any change in the capacitance, but it creates a barrier, a boundary, so that we could only fill, for example, the bottom half. So this is a half-filled parallel plate capacitor with some dielectric kappa. So the space between the top plate and the layer separating the dielectric is d over 2, and the same with the bottom layer. This is starting to become very familiar now. Two capacitors connected together in series. The top one, C1, has a capacitance equal to epsilon naught times A divided by d over 2, and the bottom one, C2, has a capacitance kappa times epsilon naught times A over d over 2. So the equivalent capacitance is equal to epsilon A, 2 epsilon A over d multiplied by 2 times kappa times epsilon A over d. And the denominator is 2 epsilon A over d plus 2 kappa epsilon A over d. Or in other words, 4 kappa epsilon squared A squared over d squared, all divided by 2 epsilon A over d times the quantity kappa plus 1. So one of the epsilons cancel, one of the a's cancels, one of the d's cancels. We can cancel the 2 and the 4 to make this just a 2. So we've got the equivalent capacitance is equal to 2 kappa epsilon A, 2 kappa epsilon A divided by kappa plus 1. Oh, and I'm sorry, don't forget this d. Or in other words, it's 2 kappa over kappa plus 1, all multiplied by epsilon A over d. So the equivalent capacitance is equal to 2 kappa over kappa plus 1 times the original capacitance. Let's see if this equation is correct. Well, what if this really is just air? What if the bottom layer is the same as the top layer? Then the kappa value would be 1, so we'd have 2 times 1 over 1 plus 1 times the original capacitance, which is 2 over 2, and so yeah, we would have no change in the capacitance. So I think we've got the correct equation here. That's not the only way to half fill a parallel plate capacitor. We could make some boundary that runs in this direction. Now that can't be a metal layer. If that was a metal boundary, then it would just short circuit the two plates, right? It would allow them to discharge, so maybe there's some plastic barrier in this case. And then we fill halfway with dielectric. Okay, well now this is no longer two capacitors connected in series. It's as if we have two capacitors that are connected in parallel. Right? We can imagine cutting down the middle and then pulling these apart, and we would have one capacitor with the same separation, D, but now half of the area. and then another one, again, with a separation of D, filled with dielectric of value kappa, and also with an area of A over 2. And they're now connected in parallel. So the equivalent capacitance would just be equal to C1 plus C2, where C1 is equal to 1/2 of C naught, right? Same distance, filled with air, but half of the area. So half of the original capacitance that was epsilon A over D. And then our other capacitor C2 would be kappa times 1/2 C naught. So our equivalent capacitance is 1/2 C naught plus kappa over 2 C naught. So our equivalent capacitance is equal to...
I didn't understand.
Oh, hey, Siri decided to interrupt us. The equivalent capacitance is equal to kappa plus 1 over 2 times C naught. And again, let's imagine if it was filled with air, we would have 1 plus 1 over 2, which is 2 over 2. And so, once more, I think we might have derived the correct equation. Okay, so just some interesting material on how dielectrics can fill the space between the conducting surfaces of the capacitor. They don't have to fill it all the way. And in fact, I'll leave you with one last thing to consider. What if we had the spherical capacitor? Oops. Bear with me as I make a copy of this. And in one case, we fill it halfway with dielectric. So we find some membrane that we can separate the space between and fill it halfway with some dielectric. With the value of kappa. Or we find another way to fill it halfway. Take a membrane like this and fill it halfway with dielectric. Can you determine how the capacitance changes in case number 1 versus case number 2? Can you figure out in which case it's effectively like two capacitors in parallel, and in which case it's like two capacitors in series? So, food for thought, and as always,